in the last few classes, we have been discussing about angular momentum, right? And what we're actually talking about in the previous few classes is actually the orbital angular momentum. And we have found the eigenvalues of the angular momentum operator, at least two of them, right? The others, they do not commute, so we can't get the same eigenstate. And then we have shown in the previous class that the eigenstates, if you want to get a position representation, they actually correspond to the spherical harmonics. So they are related to the spherical harmonics that was mentioned a bit earlier when we were talking about the hydrogen atom, right? And today we're still talking about angular momentum, but it is a different type of angular momentum. Here we call it a spin. So to make sure we understand the difference between the two, am I recording? Yes. Yes. A bit lag. Okay. Let's continue for the moment. Then probably the internet is causing problems again. Let's hope I stay connected. For now, let me just at least write. Let's begin writing something. What I was going to say is to make sure we understand the difference of these two types of angular momentum we are talking about. So like I was saying in the last class, we have been finding angular momentum, the L, M, all this kind of thing. All these are talking about orbital angular momentum. Okay, and this is in contrast with the spin angular momentum. So when we are still in the classical picture, it is easy to imagine this, because when we are talking about orbital angular momentum, it is usually referring to some particle in an orbit around an object. So it is going in some orbit, right? So this is the particle, and this is the center of the orbit. So usually it's the nucleus, like the hydrogen atom is just one proton or other things, whatever it is. There, if it's going to an orbit, then we are going to have an orbital angular momentum. Using the right hand rule, this is the axis of the orbit, and we have, this was what we have been calculating last time, right? But the point I want to emphasize here is this is the classical picture of the orbital angular momentum, right? And it is usually defined where related to something that is outside of the particle. So it's usually defined relative to another particle, right? Like the nucleus here, right? So for example, nucleus and etc., whatever this is, right? Actually, we only solved one example, hydrogen atom, so far, right? So far, but it could be for other things as well, just that the Hamiltonian are more complicated. But the main point is the axis of this circular motion is outside the particle. So axis is away from the particle. Okay. So that is in contrast to what we are going to study in detail today. In detail today is what we look at is we look at the particle itself. So if I look at that particle itself, we zoom in, then this is, well, in this example, this is our electron, right? So our electron is, I'm drawing a classical picture, right? Let's pretend our electron is a sphere, but actually in real life, electron, to the best of our measurement, the electron seems to be exactly literally a point particle. So the radius of electron is 0, not just very small, it's really 0. But in any case, that is for other, there's a discussion for another day. But this is, again, we're imagining this as a classical picture of something that is rotating, right? So we have a rotating rigid body. This is a classical picture. And anything that is rotating, it will have an angular momentum. So this is an angular momentum for a particle that is rotating. This is an orbital angular momentum where the axis is outside the particle. So this is kind of two different things. Both are angular momentum, but they describe different situations. So since they are different, we should use a different symbol to represent the spin angular momentum. So we'll just call this S. Okay, so this is the spin angular momentum. And because this is the axis is with reference to the particle itself, it means that this is an intrinsic description. That means this quantity is part of the particle itself. It is not relative to another particle. This one is with reference to other particles. So maybe the particle is doing this, then you got this thing, some angular momentum. Then if you replace the nucleus with something else, then you got some other angular momentum. So that one is dependent on external systems. But this one is really just the particle itself, and it is, as we will see later, and also the video just now was explaining, it is something that is very fundamental. And it's kind of like revealing something very fundamental about nature, about quantum mechanics, right? Like about basic fundamental concepts about physical quantities, which is the angular momentum here. Okay, so this is intrinsic, like I said. Therefore, it's fundamental. That means we no need to refer to other objects, so no need to define another particle or axis or some external system. Okay, so it's really isolated. So that means if we study the spin angular momentum, we are really studying the fundamental nature of that particle itself, not like a mixed, like combination of system that is almost towards chemistry already, right? So the hydrogen atom that we study is actually like halfway between chemistry and physics, because the orbitals will give you all the periodic tables and things like that, right? So now we go to something very fundamental. Okay, so that is the topic for today's subject, the theory of spin. So to begin, let us discuss very briefly the general theory of spin. Right, so this is 6.2.1, and to kind of bring the concept coming from something familiar, let me emphasize what did we do in classical mechanics, right? So in classical or Newtonian mechanics, and even for those taking theoretical mechanics this semester, you will deal with angular momentum that's way more complicated, right? But even with just mechanics last time, we define our angular momentum to be I omega, right? So this is just Newtonian mechanics, and when we were so this is the moment of inertia. And actually L is the general symbol that we use in mechanics, but now this is specifically L, this is S. So now we call this S. Okay, but now we want to talk about spin, right? And when we want to talk about spin, well, how do we calculate the angular momentum of this object? It is something related to I omega. But for point particles, because point particle is by definition point zero size, so for point particles, if it's zero size, then the moment of inertia is zero, right? So that means if I is zero, then you get zero spin. And in classical mechanics, we can easily imagine, because the objects of zero size cannot rotate. Right? If it's a point, so what does it mean by rotating? It's just one point. It can't do anything, right? It can just move. Okay. You need some size to say that it's rotating. So on the left side is going this way, on the right side is going the other way. So you need something of a finite size. But the surprise, or the surprising thing about quantum mechanics is, even though objects have zero size, it can't rotate, but it still have angular momentum. So that is the first weird thing we encounter. So kind of the first weird problem. And that is not really, that is no longer weird if we remind ourselves that here we're talking about angular momentum. Size is related to the moment of inertia. Right? So the angular momentum itself is something that is, it is a fundamental physical quantity and is intrinsic to particles. Okay? Oh, you realize the inertia tensor, right? Wow. Okay. Yeah. It's a mess, okay, right? It's a matrix, if I remember correctly. because you need to define your moment of inertia with reference to all your XYZ directions. So yeah, so as I was saying, in quantum mechanics, so I hope I'm not lagging anymore. So point particle has zero spin, but in quantum mechanics, point particle still have spin. Okay, and what we will see here is that it has spin, but it must be discrete values. So almost feels like a compromise. Okay, so yes, how do we now we start to establish our theory of spin, and what we are going to do is to study the theory of spin in the same way we study the theory of angular momentum. So that means we want to define the spin operators. Okay, so just like angular momentum, spin is an angular momentum. So it is in classical mechanics, it is a vector with x, y, z components because it is telling us it has a magnitude and has a size, right? By the way, I kind of say in relation to this, right? How come point particles still have spin? Is because, well, in classical mechanics, when we are talking about the spin angular momentum, this is related to how fast the thing is rotating, right? So the faster it's rotating, the larger the magnitude of this vector, and the direction tells us the direction of the axis. But in quantum mechanics, velocity doesn't really make sense anymore, right? So angular velocity also cannot be properly defined, right? So initially in classical mechanics, angular momentum is defined from velocity, but now velocity doesn't exist in quantum mechanics, but the angular momentum do exist. So from this lesson that we learned is actually, now to think back in classical mechanics, we should actually kind of like look at things the other way around. Angular velocity came from velocity if we have the classical setting, but when we go to quantum, this thing no longer exists anymore, but this thing is still there. Okay, so in any case, let me write down the XYZ components. Okay, and just the same story as last time. If we start with a classical mechanics quantity, which is a vector with components, and if we want to go to the quantum mechanics, we change this into operators, right? And also we are just like the angular momentum, we want to consider the length squared of this quantity, so it's sx squared, sy squared plus sz squared. Okay, so now we treat them as operators and we begin establishing the theory. So luckily for us, right, we can do a bit of shortcut because we shall assume that they are exactly the same concept as angular momentum L last time. If it's the same concept, then the eigenstates and eigenvalues, all of those should be the same. Am I right? So if it's the same, then we just carry over the results. So that shall be our starting postulate. Okay, so how do we even begin discussing the concept of spin? So the first idea or the first assumption or first postulate that we try to make is that, well, it is still an angular momentum. So that means the operator should behave the same way as the L's, because L is also angular momentum. So it has the similar structure for commutators as L, right? So we are kind of making a jump here, right? This is kind of like a slightly non-trivial thing, because when we talk about orbital angular momentum, right? Orbital angular momentum, we can say that this is R cross P, right? So therefore you got H bar over I R cross the del operator, right? And from here we calculate the commutator, and the formulas for commutator came out because there's a commutator between momentum and position, right? So we express everything in terms of p and x, and then we get the commutator. But here, right, there's no such thing as p anymore. Okay, there's no such thing as p anymore. So this postulate is a bit of a jump. Okay, so even though there's no p, but let's say, what if it's the same as your L? So same commutation structure. That means the commutator with xy, right? Last time we call this L, x, L, y, and the commutator is going to be I, L, z. So now we change all the L into s, right? So the same story for s, y, s, z. You got I, h bar, s, x, and then similarly s, z, s, x. Your commutator gives you an s, y. Okay, and then we're going to do the same thing to define the ladder operators. It works the same way here as well. So we can define the ladder operators, which is sx plus and minus I, s, y. And once you define the ladder operators, we also want to find the commutators, right? So it is plus minus, I forgot, plus minus h bar s plus minus, right? We needed this to find the eigenvalues last time for L, but now just change everything to s. And also you can also check that s squared commutes with everybody. Excuse me. Okay, so yeah, so far everything is the same. So since everything is the same, then we don't need to repeat everything again, because we spent one whole class doing it for L, right? So we got the results already. We go through the same story, right? So similar story. So what we found was, we encounter exactly the same situation. None of these commute with each other, so we can't find the same eigenstate for x, y, and z at the same time. Instead, we find the eigenstates of s squared and sz, because they commute, so they have the same eigenstate. And through these eigenstates, we study the physical properties, and that is what we want to do, right? So you could have done the same thing last time with, instead of z, you choose x or y. It's the same thing, but by convention, we standardize, everyone look at sz. Okay, so they have the same eigenstate and the same structure. And so therefore, let's call this, let's give it a name. What shall we call this? So the eigenstates should be some cat, right? And it's going to, instead of Lm, I'm going to call this S. And then there's a M was already used by the orbital angular momentum, so let's call this ms. Okay, so because everything is the same, so you're going to get the same formula and all those things. Okay, and just to emphasize one more time, this is not the same as the L and M that we got last time. Okay, and the reason is because they are describing different things. Okay, because this part here, this one is describes what is the state of a particle going in an orbital motion around an object. Okay, so this describes an orbit of a particle. Okay, so it's a different story, and the big difference here is, like I said, because it's an orbit, right, then the position is relevant, so we can actually have a position representation. Right, so we have found this in the previous class, right? So these are the spherical harmonics. So we can express this as a position of x and y, because this is describing the position of the particle, right? So we are talking about how the particle is moving in space, right? But this state here is just describing, yeah, so this s vector, right? So a spin of a particle. So this is what we call the spin angular momentum. So it's just talking about one particle alone. What is the angular momentum? Therefore, there's nothing to do with position here. Okay, so this is why even though both of these are angular momentum, they have the same commutation structure, but the context is different, right? Here we can talk about what, because it's an orbit, so we can talk about where is the particle, right? What is the position of the particle? Here it's just talking about one particle, so nothing to do with position, right? It's just one particle just there, and then we just want to talk about the angular momentum, so nothing to do with the position. Okay, so this is the different states, but the commutator are the same, just that the eigenstates are different. The commutator have the similar formula, right? Not the same, but the similar formula. So because the commutators obey similar formulas, the eigenstate formulas, the formulas for the spin states will be similar as well. Okay, so what do I mean by that? Well, because these are supposed to be eigenstates of s squared and sz, right? So therefore, what is the answer after you add s squared on it, right? What we got was the h bar square. Instead of ll plus 1, now is ss plus 1. Am I right? And then it is the eigenstate of sz, so if you act on this here, then is h bar times m, but now it's ms, right? So sms. Okay, so same formula. And also the ladder operator will increase and decrease the value of ms, right? So if I act on ms, then the formula, we have found the formula last time, but using L, but everything is the same, so what we got is this one, right? So plus minus 1 square root, and then ms, right? And if you there's a maximum state which is ss, you're going to get 0, and there's a minimum state which is s minus s. If you go downwards further, you just get a 0, right? And the same reasoning applies as last time. What are the possible values of ms? Ms can go from the minimum until the maximum, and the possible values of s is integer over 2. Okay, so everything is the same, right? So suddenly, yeah, we kind of finished the story. Basically copy paste the calculation from last time, the results will be the same. Okay, so does anyone have any questions so far? How's my internet? I think it looks good, I think. Am I still recording? Yes. And I'm recording here. Okay, so yeah, basically we have kind of settled the theory of spin already very quickly, but of course there's gonna be more things to discuss. But this part here is a bit interesting, right? The L last time is integer over 2. Like I said, for the hydrogen atom, L can, because L must be a number that is less than n, right? It depends on the radial wave function, it depends on the energy level and all those things. So it depends on the external system. But for this time, we are talking about the intrinsic property. So this value, the value depends, because it's intrinsic, so what else can it depend on? It depends on the type of particle. Okay, so we are kind of like going close to particle physics already, which is actually an advanced subject, but we can already say a few words about here, like what type of particle am I talking about, whether it's an electron or a proton, quarks, gluons, bosons, all those kinds of things, right? So I can kind of list you a few examples. Oh, by the way, if the integer, it depends on this thing, right? So that if there are two types of particles, well, not two types, two categories of particles, and these are the important categories because they already affect what you have been learning in thermal physics. and so on and so forth, right? The Fermi-Dirac statistics and the Bose-Einstein statistics, and that come from the type of particle we are talking about. So if it's an even number over 2, right? So that will just give an integer, right? These are what we call bosons, named after Bose, the Indian physicist. And if this is an odd number over 2, then you just get a half integer, right? And this is what we call the fermions, right? Bosons and fermions. So there are two types, and bosons are the type of particle that cause, like, we have like drastically different phenomena depending on the spin. So if we are bosons, then multiple bosons can occupy the same state, but multiple fermions cannot occupy the same state. That is the main reason why we got the hydrogen we got the chemistry periodic table, because your electron can only is filling up the orbitals, right? If electrons are bosons, then you don't get a periodic table. All the electrons can collapse into the same orbit, then you just get one type of element all the time, and then all the chemistry all gone, right? If electrons are bosons. So these are the two categories. And just to show you some few interesting examples, so S can be any number, right? So I'll start from 0, any number integer over 2. So if given a certain S, then there are the allowed values of ms should be from minus s to s, and I'm gonna show you some examples that we know, right? So let's start with S0, right? So S0, then ms can only be S0. So this is a spin 0 particle, right? So spin 0 particle usually corresponds to scalar fields, and an example for this is the Higgs boson. Is it spin 0? Suddenly now I'm not sure. Yeah, I think it's spin 0. Yeah. So the Higgs boson, right? And in theoretical physics, in a lot of things, generally scalar fields. Yeah, Higgs boson is a scalar field, so it should be spin 0, I think. Suddenly I can't recall exactly. And then spin half is a very important one, because all our important particles are spin half, almost all of them, most of them. So when spin is half, ms can go from minus half to half, right? And yeah, those our important particles are all here. So electron is spin half, a proton is spin half, neutron is also spin half, right? So these are examples of spin half particle. What about spin 1? So does anyone know an example of a spin 1 particle? So a spin 1 particle, if it's 1, then ms have 3 possible values, minus 1, 0, 2, plus 1, right? Was there a question? Higgs boson spin 0, right? Yeah. Okay, yeah, thanks. Yes, chemistry table come from quantum mechanics. Yeah, it does. It's because of the atom and all this, they satisfy Schrodinger equation. So sometimes people say, right, the Schrodinger equation, the entire branch, the entire field of chemistry is contained inside Schrodinger equation. But of course, why chemistry is a separate field is because, remember, when we solved just the hydrogen atom, the simplest chemical element, we took so much effort just to solve it, right? Hydrogen atom, haven't even got to helium yet, right? What if there's 2 electrons orbiting? So that's why it becomes a very difficult field. So the way to do it is, yeah, the chemistry people know how to do it, right? I don't, well, the physicists can't really. Example of a spin 1 particle is a photon, light. Okay, so light is a spin 1 particle. And then what if it's 3 over 2? So 3 over 2 ms can take from minus 3 over 2, half, 0, half, 3 over 2. And so the example that I do know, right, is a bit speculative. So one example is the gravitino. So this is in supersymmetry, or supergravity, and it is the super partner of the graviton. So this example has not been discovered yet and probably does not exist. So there is a theory called supergravity, and it is an idea to incorporate incorporate kind of in some way gravity with the other parts of quantum field theory. But they predicted the existence of this kind of spin 3 half particles, but so far as I know, I haven't been keeping up to date with the papers, but haven't been discovered yet. And then the spin 2 is there is another example that we know. Well, but when if it's spin 2, then ms can go from -2, -1, 0, 1, 2, and it is the graviton. Okay, so graviton is the particle for gravity. We do not have quantum gravity yet, but if you can quantize a theory, then you have a particle related to the force, right? So electromagnetic force corresponds to the photon, right? And then the gravitational force, if we can quantize it, it should be a graviton. So we do not have a theory of quantum gravity yet, but if it exists, we do know already, right? Whatever theory it is, the graviton should be spin 2. Okay, and also it is the fact that it is spin 2 is consistent with the observations of gravitational waves and things like that. So so far we know this much, but we can't really deal with it any further, right? Depending on what kind of theory of gravity that we have. So all these are kind of like the catalog of the different kinds of particles, and they are described by the spin. So it's fundamental, right? It's fundamental, and it explains what kinds of particles that can exist. Okay? Yeah. What is scalar field? Oh yeah, you guys don't know what is scalar field. Never mind. Then forget it. Just remember, just think of it, the Higgs boson. Yeah, just Higgs boson. What does spin 0 half 1 means? So at the moment, we don't need to think too in the sense that, remember, this is it is just the possible it's just the possible values of this number s, right? So s is the integer that if you calculate this is the eigenvalue of s squared, and if you calculate this, ms is the eigenvalue of sz. So for now, we don't have much meaning yet. It just means that it is just this number, so nothing special, right? Whatever this means, all these are just to tell you some interesting story. We don't need to think too much about what this means. Okay, but maybe it will be more clear if we study a specific case in detail, which is the next section, 6.2.2. We will be talking in detail about spin half particles. Okay, so now, I think after we go through this, you can kind of get a better idea of what the spin means. Okay. What phenomena will happen? Okay, so yeah, so this we will answer this question in this part. Okay, so right now, at the moment we don't know what the spin means, right? We just know all these formulas. Okay, but what we do know is we are talking about the spin angular momentum. But for now, yeah, for spin half, right? Spin half is s equals to half. Okay, when s is equal to half, that means ms can be minus half or positive half. Okay, so there are only two eigenstates in this case, right? So if s is half, there's only two eigenstates, which is just what the first letter is s, ms, right? So it's either is minus half or positive half. Okay, so that is basically what this means, right? What is the eigenvalue of s squared? So the eigenvalue of s squared, let's calculate. Well, the formula was this, right? It is s ms, and then the formula was h bar square, what was it, ss plus 1 right, SMS. So if I calculate the eigenvalue of plus half, right, then what you get here is, well, actually plus and minus is the same eigenvalue, right? So let's do it both at the same time. Is h bar square, and then this is half, and then half plus half is 3 over 2. So you get 3 over 4, half plus and minus half, right? So the eigenvalue, so what does this mean? That means the eigenvalue of s square is 3 over 4 h bar square. Okay, okay, so now we can try to answer what does this mean, right? This is the number that we got because the s is half, right? And remember the postulate of quantum mechanics. What does eigenvalue means, right? Eigenvalue means it is the outcome when s squared is measured. Okay, so in ordinary everyday language, that means what this means is that the length of s, right, and then square is 3 over 4 h bar square. So that tells us the magnitude of the angular momentum. So I guess that kind of answers the question. What does the spin half means? Well, spin half, this s will give you this eigenvalue, right? So the eigenvalue 3 over 2, and this is the eigenvalue of s squared. By the postulates of quantum mechanics, eigenvalue of an operator means you get this result when you measure this. So what are we measuring? We are measuring the magnitude of the spin angular momentum. So the angular momentum is a quantity, right? We have used this quantity since mechanics, angular momentum. And the magnitude of this angular momentum is 3 over 4 h bar square. Okay, so this part we got already. And how about the sz, right? So sz is also and this is also an eigenstate of sz. And if I use the formula, well, let me remind ourselves what is the formula. ms, it will give you h bar ms s ms, right? So that means if I measure this, I will get a positive h bar over 2, half, right? And then if I measure the other state, I will get minus h bar over 2, half minus half. Okay, so this state corresponds to sz having a value of h bar over 2, right? Measure, and then this part, if you measure sz for this state, you will get a minus h bar over 2. And what is sz? Sz is the z component of your angular momentum, right? So always remember, we are talking about an angular momentum vector over here. So we got xyj component, xyz components, right? So we got the length and we got this measurement. So we got these two pieces of information, right? And we done the same thing for L last time, right? We can draw the vector now, right? So we can draw the xyz axis of the vector, right? So if I plot the xz component, so this is x, this is y, then I want to draw an angular momentum vector. So it's a vector, and what we do know is the length square is 3 over 2 h bar square. So let me draw a circle of root 3 over 2 h bar. So the vector is this length, so it's somewhere on this sphere, right? So this is negative root 3 over 2 h bar. Okay, so the vector should having this length somewhere, right? And but what is the z component? Well, there are two possible z components. One possible z component is the outcome is h bar over 2. So h bar over 2 is somewhere smaller than this, so it should be roughly around here. If you calculate the numbers, root 3 over 2 is, yeah, it is some number smaller. I'm lazy to get a calculator, but positive h bar over 2, negative h bar over 2 is down here. Okay, so this is my z component of this vector, and this is my z component of this angular momentum vector. So now I can try to draw my angular momentum vector. It is my angular momentum vector is somewhere like this. This vector. So this is the vector, right? For the state half-half. Okay, so I draw the x and the z, but the y and the length and the z I can draw it exactly, but x, y, and s, x are not eigenstates of this operator. So because they are not eigenstates, then we can't get specific eigenvalues. So we don't know what is the y and x component. So it could be pointing anywhere along this cone, right? As long as the z component is fixed, the x and y component is not fixed, so it could be anywhere along this direction. Okay. So the same story goes for the other case, right? So for the other part is negative half. So this is the state of half minus half. That means my particle is having this type of angular momentum that is looking like this. And same story again, the x and y directions are not fixed, so it could be pointing anywhere, right? So I don't know which direction to draw, so it could be anywhere along this cone, right? So this one is just purposely drawing one example, but it could be any direction for the x and y. Okay, so this tells me my angular momentum vector. So but if you still want to imagine what does the state looks like, we can't imagine this anymore. But if we try to draw the classical picture, right, that means my electron, if my electron is a sphere, it is rotating with this axis. So using the right hand rule, the rotation is this way, but this is the classical picture. Okay, but quantum mechanics, you can't get this picture anymore, but at least, you know, it kind of helps us imagine something, right? So this is, it is rotating this way, so the spin is pointing up, and then this one, the classical picture is pointing down. So my if my electron is a sphere, then my rotation is the other directions, right? So one is like clockwise rotation, the other is anti-clockwise, but the axis is pointing like this way. Okay, so this is the classical picture. Okay, but since there are two states, so even though it's not pointing perfectly up, but it is roughly up, so usually we denote this state by the up symbol, and we denote this state by down symbol. Okay, so actually, to again answer the question, what does this S half means? It is actually a state that we encountered before, up and down, right? When we were doing the Stern-Gallup experiment. So we denote, right? So we are calling this half-half, but since there's two of them, instead of writing so long, right, let's just write this, right? And then the other state is, because it's roughly pointing down, so we point this down. So these are our two states, and we call this the spin up state, and we call this the spin down state, right? And we did this in chapter 2 for the Stern-Gallup, right? So Stern-Gallup, right? And also last time, right, we were using the matrix form. We often use the matrix form. So why not use it here too, right? Since everyone is more comfortable using matrices, right? This is like a new weird symbol for this course that you guys are learning for the first time, but it's just 1, 0, right? And then this one is just, the spin down is, last time we called this 0, 1. So actually, this is something we are perfectly familiar with. Okay, so that was basically the theory of spin half particle. So these are the two eigenstates. So let me check what's the time now. spin 0 photon and plus minus 1 photon. It's just the different states, lor. Yeah, it's just that it's just the different states. So the answer is the same as this. So what's the difference between a spin plus half and minus half is the angular momentum, right? It's the angular momentum directions. The z component is here, the z component is here. For the spin 1 photon, they got 3, right? So for the photon, right, it is the s is 1, so I got 2 states, minus half, 0, and positive half, right? So we can do the same story here. So that means this, my angular momentum vector is like pointing down, and then this the z component is 0, so it's like horizontal or in the xy plane, and then the angular momentum is pointing here, right? So this is my angular momentum vectors for the photon. Yeah. So interesting, right? From commutators, we suddenly encounter something that we are familiar with. Okay, and for photons, and also why does photon spin 1 is also something that I can't answer yet. We need to go a bit deeper into the answer to this requires something more deeper, which is not in our syllabus, right? But right now we are learning the basics. So the basic, we start with the spin half particles, and yeah, only 2 states. So we shall try to understand that first. Okay, any other question? What is the Higgs? Oh yeah, just now you're saying, right? Yeah, so the Higgs boson is the Higgs boson is a very famous particle. It was discovered in it was just discovered in 2012, right? So this one it was the last particle. So in particle physics, right? So right now we have a kind of like more or less complete theory of particles. We understand all the particles, how the particle behaves, almost everything except gravity. So as long as gravity is weak near the Earth, even moving close to the speed of light, special relativity, we understand the full theory of particles, how they scatter, how they collide, whether they decay or not, radiation, all these things. So all these things are called the standard model. So this is the last particle discovered of the standard model that was discovered. The last important because in order to fill in the gap of many interactions, you need to have this particle to interact, and it was discovered in 2012. So it actually feels like it's actually a long time ago now, right? But I remember, like, I was a student like way before 2012, and everyone in physics was like, okay, will we discover the Higgs boson or not? At that time, it was like a very tense situation, right? A very dramatic situation. Will we discover it or will it not? Is it exist or does it not exist? If it doesn't exist, then the standard model must be modified. But finally, in 2012, they found it. So the standard model is more or less confirmed. And since then, yeah, we are using the standard model. So it was like a big news back in 2012. So that was the Higgs boson. Page 1, page 2. Okay, any other question? So now that we are talking about the spin half particles, well, we got the states already, right? And what I'm going to do next is, since we are comfortable in the matrix form, let us express everything in terms of matrices. So we want to find Sz in a matrix formula and S squared in a matrix formula. We shall start with Z, S squared. Okay, so the first thing that we want to do is find the matrix form of S squared. So we find S squared first, and then we find the others and SZ and later. So let's start with S squared, right? So yeah, we started with this equation, right? So we got half, half, and then what we got was half first. It is 3 over 2 h 3 over 4, right? H bar square, right? Half half. Okay, and we are saying that this is the spin up state. So 3 over 4 h bar square, the spin up state is the eigenstate of the operator. But the spin up is a matrix 1, 0. What is the corresponding matrix from this? So it should be quite an easy problem to solve. Let's solve this, right? In order to find the matrix form, this is an unknown matrix. So let me give them unknown symbols A, B, C, D, and we want to figure out what is A, B, C, D, right? So the equation S square up 3 over 4 h bar square up means the matrix A, B, C, D times 1, 0, and then this is 3 over 4 h bar times 1, 0. Okay, so this one can tell me what? Well, this tell me A plus 0 and then C, and then this is 3 h bar over 4, 0. Okay, so I conclude that A is 3 over 4 h bar and C must be 0, right? And then how about, well, how to get the others? Well, I got another eigenstate. S squared down still gives me the same eigenvalue, right, as we have shown in the last time. So this is just A, B, C, D, 0, 1, and then this is 3 over 4 h bar square, 0, 1. So if you multiply out, you get B, D, and then 0, 3 h bar square over 4. So that tells me B must be 0 and D must be 3 h bar square over 4. Right, I forgot the square here. So I got A, B, C, D now. So from this conclusion, I found that S square is a matrix that is 3 h bar square over 4. B is 0, C is 0, and then 3 h bar square over 4. So I can pull out the factor of 3 over 4 h bar square, 1, 0, 0, 1. Right, so I found the matrix form. It is just the identity matrix times 3 over 4 h bar square. Okay, so I found the matrix formula for this. Okay, and related to this, because S is Hermitian, I can also do the Cat-Bra expansion. So let's find the Cat-Bra expansion as well. Right, since S squared is Hermitian, so I think this one forgot already, right? This is kind of a long time ago, back in chapter 1. For a Hermitian operator, the eigenstates form a complete set, right? And then from a complete set, we can do a spectral decomposition. So that means if I know the eigenstates and the eigenvalues, I can expand this in terms of the eigenstate and eigenvalues. It is the sum of the eigenvalue times like this, right? So this one is something that can be proven in linear algebra course, just with different notations. And did we? Yeah, we used this quite a lot last time, back in chapter 1. But right now we do know, right? So there's two states, up and down. For the up state, the eigenvalue is 3 over 4 h bar square, up. And for the down state, it's still the same eigenvalue, down. Right? So therefore, S squared, I can factorize 3 over 4 h bar square, and then got up, down, right? And because the eigenstates are complete, up, down, Cat-Bra, they add up, they do become the identity matrix, right? So we have found the different ways to represent our S square matrix. This is 1. Okay, so this is our first result. We have found the matrix form for S square. Okay, what's the time now? Okay, so I think now is a good time to take a rest, because we will do SZ later, right after this. We don't need to find the matrix of L square. Yeah, we don't need, because for L square, right, why didn't we do it? The reason is because when we are doing the angular momentum, the states are the wave functions, right? So in position representation, so it doesn't really make sense to find the matrix form, right? That is the main difference, because for position wave functions, my variables are continuous, so the operator will become derivative operators. So we can't really find, right? And so we don't really bother to do this. But for the case of spin, because spin has a low dimension, only have 2 eigenstates. Since they have 2 eigenstates, then we can use this form, right? Not continuous function anymore, but just 2 states, and therefore we can write the then it is more useful to find the matrix for S squared rather than L, right? Because of the intrinsic kind of thing. You can, if you want, for certain energy values you can, but not to say it doesn't exist, but it's not very useful. So even if you find it, it's not being used for calculation. This one, right, we will show later that it will be the same operators that we did in the Stern-Galak, the magnets, the flippers, and all those things. It will be useful here. Yeah. So in any case, let's take a 10 minutes break. Interesting, right? I find this interesting too. Yeah, it's pretty fun to play around with the concept of spin. But let's take a 10 minutes break, and we come back in 507. So let me stop the recording first. Start the recording here. Yeah, so now we can really see that we're starting to go into really interesting things already, right? Because now that we just started to learn quantum mechanics, but we have kind of like have the sufficient language to appreciate like all the weird and interesting phenomena that was related to all these things. So all these are under what we call the quantum field theory, right? So you learn all about this in quantum field theory. So just now I misread Iran's question. So what you're asking is photon. Whether you're asking the Higgs interact with gravitational field or the photon. So I think, yeah, photon doesn't interact with the Higgs field, but it doesn't interact with gravitational field directly as well. So actually they do not interact with neither, but the gravitational field is interesting because it will curve, according to relativity, it will curve the space-time. And photon because the space-time is curved, then the motion of photon will also be curved. And that is the indirect interaction, right? So in quantum field theory, the direct interaction means it does there is a special exchange of particles between the two of them. So 2 electrons, right, they directly interact because we learned this in Coulomb's law. But if you incorporate quantum mechanics, we explain Coulomb's law because the force between the two happened because they exchange the photons. And that is the interaction. And yeah, so the way to calculate this, you need to like do Feynman diagrams. You need to do more complicated Bras and Katz calculation and things like that. So I guess you have that to look forward to in the future, right? But meanwhile, if you are interested, there's plenty of those videos about Higgs boson, because it was, like I said, it was a big news back in 2012, and there will be a lot of YouTube videos about that as well, or articles online. Okay, so who asked, Jason? Was it? Yeah, you were asking, is spin related to the Pauli matrix? Exactly, yes, because we are actually going to derive this right now, right? So what we have found was, wait, I forgot where were we? Yeah, so we have found the matrix form of S square, and the next thing that we want to do is SZ, and that is the spoiler. SZ is actually the Pauli matrix times a constant. So that's the next thing that we want to do, finding the matrix form of SZ. Okay, so that is the that is kind of like another plot twist. That something that we've been dealing with is actually something we have seen before, right? So to do this, we shall let the same method as last time. As for S square, it is an unknown matrix, so let's call this ABCD, and we need to figure out what are the elements ABCD. Okay. I'm recording, right? Yes. And my screen is sharing. Yes. So we start with, firstly, we start with the equation that we do know. What does Sz do? Well, this is the eigenstate of Sz with the eigenvalue of plus h bar over 2 back to the state. So if I change this into a matrix expression, we got ABCD times 1, 0. This is h bar over 2, 1, 0. So if I multiply out, it's just AC, right? A and C. And then this is just h bar over 2, 0. So we conclude that A is h bar over 2, C must be 0. Okay? And then the next equation that we have is Sz down, right? Sz down, it will give me a negative of this down. So if I change this into matrix form, ABCD, down is 0, 1. So I got h bar over 2, 0, 1. So this is 0 and B, this is 0 and D, and then this is 0, h bar over 2, negative. So we conclude that B is 0, D is negative, h bar over 2. So now I figured out what is A, B, C, and D. What is the matrix form of this? Well, Sz is, the A is h bar 2, B is 0, C is also 0, D is negative, h bar over 2. So if I take out the factor of h bar over 2, I got 1, 0, 0, minus 1, right? So what is this? This is the sigma z Pauli matrix that we have been using last time, right? So this one, it just gives us the correct normalization and the correct dimension for the angular momentum. So this is just the dimensionless part. So h bar has a dimension of joule seconds. So that is the same as the dimension of angular momentum. Is it? Yeah. So we have found sigma z already. And while we're at it, we do the Cat-Bra expansion as well. Right, so this is also Hermitian. Therefore, the eigenstates are the same eigenstate here. These are complete, right? So we start with the formula like this. This is for general operator, but if it's the up state, the eigenvalue is positive h bar over 2, up. If it's the down state, the eigenvalue is negative h bar over 2, down, right? So I can pull out this factor. We have found that the Cat-Bra expression for this is just up, minus down. Okay, so yeah, so finally we have found the matrix form for sigma z, right? So it's sigma z h bar over 2, 1, 0, 0, minus 1. And if you want to write this in Cat-Bra form, you do it this way. So up, minus down. Right, so this is our Sz. Okay, and oh yeah, this is also the sigma z operator, our Pauli matrix. Okay, so that's pretty fast, right? Yeah, because we already established all our eigenvalues and states already. So it's just a matter of like re-expressing in terms of something that we already know. Okay, so what other operators are we supposed to do? The ladder operator, the ladder operator. So the next thing that I want to do is we want to find the matrix form of the ladder operators. Okay, so S plus what does the ladder operator do? So S plus, so the eigenstates that we found is not an eigenstate of S plus, because S plus is a ladder operator. It changed into a different state, not an eigenstate. But we still have a formula, right? What happens if you do a plus operator on this? We got S plus 1, right? If it's a plus, then it is ms raised by 1, right? So this will raise the ms value by 1, right? We have shown this in much detail in the previous week already, but what we want to do now is let's check what happens if you do this on the S half, and then also plus, right? So plus, if I do it on the plus half, it will become 0, so no point writing, but you get a minus half, so you got this, right? So what is the numbers here? S is half, S plus 1 is 3 over 2, so half times 3 over 2 minus ms is negative half, and then negative half plus 1 becomes plus half. So this is half, and then negative half plus 1, it will change this into a plus half state, right? And actually this one, if you simplify, this is 3 over 4 plus 1 over 4. So basically this is just the square root of 4 over 4 is just 1. Right? In other words, this was the down state. So S plus acting on the down state gives me a H bar times the up state. So this is also something familiar that we did last time, right? Instead of the H bar, except for the H bar, this is like the flipper, right? But it only flips down to up. If it up, you get a 0. So it's not exactly a flipper, but it kind of like does something similar. Okay, but so let's not be distracted. We should supposed to find the matrix form. So let's find the matrix form. Okay, so we are going to let S be some unknown matrix, so A, B, C, D, right? And then this equation tells me that A, B, C, D times the down state gives me a H bar of the up state. So this is B and D, and then this is H bar. So that will tell me that B is H bar and D is 0. Okay. Yeah, so I only got 2, but what about the other one? Let's go to the other equation. We do know that if I add this on the up state, right, so this is already the maximum. So I will get a 0, right? Remember, when I reach the maximum ladder, in order to avoid the z component to be greater than the actual length of the vector, the only way to avoid the inconsistency is to make it 0, right? We gone through this last time. For now, with the equation that we have is acting on the up state, it will just give me a 0, 0, right? 0, this one means a 0 vector. So what we have here is A plus 0 and C plus 0. And both are 0, 0. So we conclude that A is 0, C is also 0. So from this information, we found that my S plus vector is A is 0, B is H bar, C is 0, D is 0. Right? Or in other words, this is just H bar 0, 1, 0, 0. Okay, so we have found the matrix form for the plus ladder operator. Then we do the same thing for the minus ladder operator. Okay. So for the minus ladder operator let's write the full formula first. It is H bar SS plus 1. So this first term is always the same, but I'm minusing ms. If I'm minusing, then it's ms reduced by 1. And then ms reduced by 1. So if I'm talking about the half, if I add this on the plus half operator, this will give me half. This is 3 over 2 minus half, and then half minus 1 is negative half, and then this will change me into half, negative half, right? So in the end, this is just H bar half minus half, right? So everything here becomes 1. So therefore we conclude that S acting on the up state just gives me a H bar times the down state. Okay, so now we go do the matrix form, right? So A, B, C, D, up state, H bar 1, down state, so 0, 1. So this is A plus 0, C plus 0, this is 0 H bar. So we conclude that A is 0 and C is H bar. Right? And then if I act as negative on the down state, I will get a 0 vector. So I got A, B, C, D, 0, 1. And then this is 0 vector is 0, 0. So this is 0 plus B, 0 plus D. This is 0, 0. So I found B is 0, D is 0. So from this information, I conclude that S minus is 0, 0, H bar, 0. So this is H bar 0, 0, 1, 0. Okay, so I have found the S negative. Okay, any questions so far? Yeah, so what else haven't we found? We found everything S plus, S minus, and then next is SY and SX. So let's do that now. Okay, so what we want to do is we need to find the matrix form of SX and also Y. But we don't need to go through the equations again. We already have S plus minus, right? Remember what was S plus and S minus? S plus is defined to be Sx plus ISY. S minus is defined to be Sx minus ISY. So I can express this, right? So notice that if I take equation 1 plus equation 2, I found that S plus S minus, this plus this will cancel. I got 2Sx, therefore Sx is just half of this plus this, right? And I already know the matrix form of these two. So just add this in the matrix together. Right, so what was S plus? S plus is this thing, right? So it's H bar 0, 1, 0, 0 plus H bar 0, 0, 1, 0. And H bar can be factorized out. And this matrix plus this matrix just give me 0, 1, 1, 0. Right, so this is Sx. Okay, so I found Sx already. And then we do the same thing for Sy. So how to get Sy? Well, I can take equation 1 minus equation 2. So if I take 1 minus 2, it is S plus minus S negative. So this minus this cancels the Sx. This minus this gives me a 2i. So there's an I, must be careful. Right? Therefore, my Sy is 1 over 2i. S plus minus S minus. Okay? And therefore, this is 1 over 2i. The matrix form was this now minus this. So it's H bar 0, 1, 0, 0 minus H bar 0, 0, 1, 0. The H bar can be factorized. H bar over 2i. And then this is 0, 1, minus 1, 0. And let me just flip, right? So let me flip the I upstairs. So I got negative I H bar over 2. 0, 1, minus 1, 0. And I'm going to take I'm going to multiply this inside, right? So that everything outside is just H bar over 2. So what I found here is 0 minus I. Negative 1 times negative I is just positive I. And then 0. So this is Sy. So we have found, we have found everybody already. We have found Sx, Sy, X, Z, right? So let us collect all our result. Right, we are summarizing our results here. We have found Sx, the spin operator in matrix form is H bar over 2, 0, 1, 1, 0. We have found Sy, which is just H bar over 2, 0 minus I, 0. We have found Sz, which is H bar over 2, 1, 0, 0, 1, right? 1, 0 minus 1. Yeah, over here, 1, 0, 0 minus 1. Okay. So we have kind of this now we have seen, right? This is something that was familiar to us. This is actually the Pauli matrix. So in some sense, the plot twist, or the revelation behind all this is that our spin operators x, y, z components is actually constant times the Pauli matrices. The same Pauli matrices we have been using in chapter 2. So in chapter 2, I just like tell you the formula of Pauli matrices, and I just tell you what does it mean by the Stern-Galat experiment, right? I just say, right, for no particular reason, just that, oh, magnet in the z direction, it will give you the 2 beams. Magnet in the y direction, do this. Magnet in the x direction, you need this matrix. Now we actually know. We can derive the formula from the, we have derived this from the basic principles of angular momentum. Okay, so these are our Pauli matrices. Which is sigma x is just, let me write this one more time since these are important. Sigma y is 0 minus I 0. So x and y are off diagonal. The diagonal terms are 0. And this is all real. So 1, 1. This is minus I. So minus I and I here, it will make sure the Pauli matrices are Hermitian, right? And sigma z is also diagonal and therefore automatically Hermitian. And this part is real, so it's Hermitian, definitely Hermitian. So yes, we have found the Pauli matrices, right? And we revealed that the Pauli matrices are actually the h bar over 2 times the angular momentum operator for the spin half particle. This whole chapter is about spin half particle. Spin half particle, you will need 2 by 2 matrices. And if you talk about photon, right, you were asking about photon 0, 1, plus 1. I got 3 states, so I need a 3-dimensional vector space. So if you want to do the photon case, then the operators must be 3 by 3 matrices. Right, so for higher spins, you need larger matrices. For spin half, only 2, so 2 by 2 matrices. Okay, so we are at page 7. Okay, so yeah, we are almost done for this section already. Right, so that is the theory of spin. Any question? Okay. So if not, let us give you a few properties about the Pauli matrices. Right, so now we know the spin angular momentum is just h bar over 2 times Pauli matrices, and we have found the eigenstates. So even though we don't know the eigenstates of x and y, but at least we know the matrix form. So we can still do calculations based on it, right? Even when they are not eigenstates, we can still do things related to it. So it will be good to understand what are the properties of the Pauli matrices. So let us start. What are the commutators? A lot of them is inherited from the S, because we started as our starting postulate, right? S x s y is equals to I h bar s z, right? And s x is just h bar over 2 sigma x. This is just h bar over 2 sigma y, and that is just h bar over 2 sigma z. So I can factorize this out. So this is become h bar squared over 4 sigma x commutator sigma y, and then this is I h bar squared over 2 sigma z. So I can cancel the h bar, the 4 bring over, it will cancel with 1, 2 there. So I found the commutator to be 2i sigma z. Right? Yes, it came from spin. So that's kind of like the interesting way to look at it, right? We are using commutator, like just now I was saying that we were doing the Stern-Galat, we are just given the formula without really explaining why. And that is because we haven't learned enough yet. Now we learn angular momentum, we learn the spin, we know how to find the eigenstates. And then if we write the eigenstate in the matrix form, suddenly we recover we recover all our Pauli matrices. So yes, the Pauli matrices come from the concept of spin. It is the components of the spin operator, right? So don't forget, because we always go too deep into the details, but students tend to forget that, yeah, it is the vector, right? It tells us what is the angular momentum of the particle, right? So in fact, we will re-derive a few things about the Stern-Galag experiment again later. Now we re-derive the Pauli matrices first. Okay. What we have now is, okay, so you can do the same for the other commutator. So let us not repeat everything. Right. So you can do the same. Is basically you can, once you know the formula, you do the cyclic operation. Right. You just need to remember one of them. You can easily derive the others. Right. So this thing. In fact, we shall show this explicitly because we know the matrices. Since they are just 2 by 2 matrices, so it's easy to multiply them. This is the cyclic property. Cyclic property means that sigma I sigma j is equals to negative sigma j sigma I, right? For I, j, whether it's x, y, or z. Okay. What do I mean by this? Well, let's just write an example. What is sigma x times sigma y? Okay, so it's just a matrix times another matrix. So sigma x is 0, 1, 1, 0. Sigma y is 0, I, 0. Right, so if I multiply this together, what do I get? This is 0, I, right? And then this is 0, 0. This is 0, 0. And then this is minus I. Okay, so if I take out the I, we recognize something familiar. This is just sigma z. It's just I times sigma z. If I do it the other way around, what is sigma y times sigma z? Okay, so it's 0, 1, 0, I, 0. Sigma x is 0, 1, 1, 0. Okay, they're Hermitian. So if I multiply this, what do I get? 0 minus I. 0 plus 0, nothing. 0 plus 0, and then I plus 0. So it's just I. So if I take out, so notice that this is the negative of the above. So this is just negative I, 1, 0, 0 minus 1. So you just minus I sigma z. Oh, yeah, I forgot this. Cyclic I. Right. So therefore, we see that this is I sigma z, this is sigma z. So from here, we can derive the commutator again. Sigma x, commutator sigma y. What does commutator mean? Commutator just means doing this, right? So that means it's this minus this. This minus this is just 2i sigma z, right? So again, we have derived the commutator again. Right, what we got just now up here. Okay, and then yeah, so obviously you can do it similarly. You can do y, z, x, z, whatever. You get the same result. So, but we don't need to waste time showing everything again, right? So it's the same thing. What other properties does the Pauli matrices have? Very useful property. It has a unit square. Okay, so unit square means sigma x square oh yeah, I suddenly write z for no reason. You're right, thanks. Sigma x. Yeah. Supposed to do it because we want to show, okay, do it one way, but I reverse the order, right? So this is the commutation, right? If numbers, if you multiply, whether who is front or who is back, it doesn't matter. But for matrices and operators, who is in the front, who is in the back will cause a difference. And it depends on whether they commute or not. Yeah, so I'm talking about unit square. So let's square this matrix, right? Squaring means multiplying again itself. So this is 0, 1, 0, 0, 0, 0, 1, 0. Okay, so you get the identity, right? And you try the others, you also get the identity for everyone. Minus I 0, minus I 0. So this is 0, negative I times I gives you a plus 1. This is 0 plus 0. This is 0 plus 0. And then negative I again. So this is again the identity, see? And then sigma z square, still the same result. You will also get the identity, right? This is 1 plus 0, 0, 0, 0, 0, and then minus 1 times 1 is plus 1. So everyone here is the identity, right? And because this is a unit square, then we can easily calculate what was the, we started with this thing, right? So our s square was sx square plus sy square plus sz square. So now we know that this is sx, let me remind you again, this is h bar over 2 sigma x, right? So sy is h bar over 2 sigma y, and sz is h bar over 2 sigma z. So if I square this gives me h bar square over 4 sigma x square, and then yeah, same thing, h bar square over 4 sigma y square, h bar square over 4 sigma z. But all these are identity, so this is just 3 h bar square over 4 identity. And we got back the formula again. We already derived this earlier, but now we got it again in another way, right? So everything kind of like consistent. So all the puzzles fit together, right? So they all make sense. Of course, it has to, right? Otherwise, we want you will run into trouble. Okay. Okay, yeah, so don't worry. Yeah. And then here is a cool way of writing the spin operators. We can, well, since we wrote the S in matrix form, right? In matrix form, and then also we started in vector form also. So in vector form, we can also write the Pauli matrices in vector form. Because since we had, we started with this in the first place, right? So we got sx square plus syj plus szk, right? And now we have found that this is just h bar over 2 sigma x. So we just replace this, right? We have already shown all this, they are equal to each other. Okay, so here we shall, let us define, right? We will define as the Pauli matrix vector. So the Pauli matrix vector, and this is h bar over 2, right? So the s, generally to change all the s from sigma is just by h bar over 2. Okay, so from here we conclude that we can write a Pauli matrix in vector form. So sigma xi, sigma yj, sigma z, k. So people, actually those who are doing quantum encryption and quantum teleportation, quantum cryptography, they tend to express the sigma in vector form. Is way more convenient. Okay, but if the benefit of writing in vector form, right? If you are familiar with vectors, right, like the calculus Euclidean vector spaces, then there's a very handy way to remember all the previous properties that we had just now. Okay, so all the properties, right, like the cyclic properties, the unit square, all those kind of things, has a very compact version if I express everything in vectors. So let's do that now. So in order to do that, let me write the normal numerical numbers vectors. Right, so A, let's say I have a vector A, right? This is just a normal vector, like from mechanics. Like some normal vector A with 3 components. These are not operators, they are just numbers. And I need a second vector, so let's call this B. Okay, be some norm vectors, whatever this vector is, they are not operators, right? Then the properties that we got on the what we shown just now has a very compact version. So let me show you. So then the properties can be expressed in a single formula, and it looks like this. So A dot sigma, this is a matrix multiplication, B dot sigma is equals to A dot B identity plus I A cross B dot product with sigma. Okay, so it looks like a complicated formula, but it contains all the formulas that we had just now. So it's actually, well, depends on which version you prefer, whether it's useful or not. I don't know, but I should at least show you how to use this formula. Okay, so let's take some examples. Let's take, what was it? Yeah, if it doesn't satisfy, Nobel Prize. Right, we discover some gap in quantum mechanics. So let's see how to use this formula. So this is for general A, but let's say, right, A is a vector. So let's say A is just a vector in the I, just I. And then the B vector is just J, right? So I dot sigma vector, it will just give me the sigma X part. And then this, it will just give me the sigma Y part. And then A dot B is just I dot J identity. And then this is complex number I. A cross B is just I cross J dot sigma. Now I dot J, what's I dot J? They are perpendicular vectors, so this is 0. I cross J gives me K, so K dot sigma is just sigma Z. So we have generated this formula, right? So then the other way around. What if A is J instead? Let's swap the two. And then if B, so this is if, right? This is I. Okay. So the first term is A dot sigma. So J dot sigma, it will give me the J component, sigma Y. Then the second is the I component, sigma X. Then this is just J dot I, it's going to be 0. And then I, J cross I dot sigma. So that gives me negative K. So this whole thing just give me sigma Z. So we have found sigma Y times sigma X is 0 plus sigma Z. Right? So we recovered the formula. What if A and B are the same? So let's try another combination. So if let's say A is the Z direction and B is also the Z direction. Okay, so if I put this into the formula, K dot sigma gives me sigma Z. K dot sigma again gives me another sigma Z. So it's just sigma Z square. And then this term is just K dot K times the identity. And then this is the I vector K cross K dot with sigma, but K cross K is 0. K dot K is 1. So this is just sigma Z square. We recover the formula that is unit square. Right? So if you square this, if you square all the Pauli matrices, you get 1. Okay, so any question? Okay, so we have 6 minutes left. We kind of finished the spin already. The main objective for this section is just to derive the Pauli matrix. But since we have a bit of time left, let us go into the next part a little bit. Like I said, I was saying that we are going to look at the Stern-Galat experiment again. Now that we know what does the spin up and spin down means, right? So let's look at the Stern-Galat experiment again. So this is 6.2.3. we are revisiting the Stern-Gallac experiment. So this is the Stern-Gallac experiment, the sequel. Okay, and we will come. There's a part 3 again later. So Stern-Gallac is actually like it's a very useful experiment to understand quantum mechanics. Okay. So yeah. So what we have here is for the Stern-Gallac experiment, right? So the Stern-Gallac experiment, let me remind you what is it about. So it is an oven that is creating silver atoms, right? And then we have an inhomogeneous magnetic field, right? So we got the inhomogeneous magnetic field like this, right? And then this is inhomogeneous. And if you remember, like way back in chapter 2, we kind of, in classical physics, you know, the inhomogeneous magnetic field will cause a force, and then it will exert a force depending on the direction. It will cause the beam to go in different parts depending on what is the angular momentum. Now we know angular momentum is quantized, right? So angular momentum is quantized. There's only 2 possible values of angular momentum. It can either go this way, so that will give me the spin up, or it will go this way, it will give me the spin down, right? So this one is representing the angular momentum of a vector that is like pointing this way. So this is my S vector, right? And then this is the particle that the length is fixed, right? Because S is half, that is pointing down, right? So particle that is having this spin will go this way, particle having the other spin will come down. And it's only 2 discrete values. These are quantized, right? So, and we have also shown that this is the state of half-half. This is the state of half minus half. So these are the eigenstates of the angular momentum operator. Okay. So so what we have shown here, right? This is a measurement of the sigma z, right? So sigma z is Prof is calling me. So the sigma z is h bar over 2. Sorry, the spin operator is sz is half sigma over 2. So what we have here, right, is the okay, so it's you guys. What we have here is this is a measurement of the spin of the sz component, right? So that is represented by the spin half and plus half. So because this is a measurement, right, then the eigenvalues, right, we have already found the eigenvalues, which is plus h bar over 2 and negative h bar over 2 are the possible outcomes. Okay, so that is the, so this is what we have. This part is the outcome, right? So outcome, this is the h bar over 2, this is negative h bar over 2. So now what is the, so now we can go back to answer the question again. Like when we were talking about the postulates of quantum mechanics, the eigenvalue is the measurement outcome. What does that actually mean, right? And it's a bit abstract at the time. Now we know that sigma z, yeah, is a bit abstract because I just say plus or minus, and then I give you some excuse about the some z direction, right? But now we know, right? So the possible outcomes is this. So that means it the outcomes here are the is telling us about the z component of its angular momentum. Okay, so basically, yeah, so essentially now we kind of like understand the picture for the Stern-Gallac experiment already. So if we do this, we get the we get the Z components. So now if we do the magnet that is pointing in the horizontal direction, I don't know how to draw, right? So let's say this is the Y direction, right? So this is the measuring SY, right? So it will split in the Y direction, and then it will give me yeah, so we are measuring. Is there any question? Okay, so you guys are making fun of the phone call. So we are measuring the sigma. We are measuring the spin component in the Y direction, and then the same story as before. So it's basically outcome, and so on and so forth. Okay, but so what I haven't told you yet is what are the possible outcomes. Okay, physically we are just rotating the experiment. So even in a tutorial question, what do you expect to happen if the magnet is now pointing along the Y direction? And then the answer that was given at that time was not very satisfying. Is the beam split into X and Y? In some sense it is expected, but now we can actually show this. Okay, so now this is something we can show. So I think when we continue in the next class, we will measure the we will calculate. We haven't done this yet, right? Because SY and SX we haven't even measured yet. So now we haven't talked about the eigenstates or the eigenvalues. It's not the same as these two, but it's still an operator, it's still a measurement, it still should have some kind of outcome. So what do you expect when we try to measure this? Is it also two eigenvalues, and so on and so forth? So we shall answer this question when we come back on Monday. By the way, Monday, right? So Monday is tutorial day. There's still some of you who haven't presented yet, so try to present something. We are in week 11, is it? We are in week 11 now. So we are running out of opportunities for presentations, right? So important thing to remember, presentation is part of their continuous assessment. So they got score. There's a score related to it. So do try to present, okay? 15, right? So 15 is the final week. Yeah, 15 weeks. So 15 weeks. Okay, so yeah, so take note. Also assignment, yes. No, week 15 is the last lecture. Week 15 is the last lecture. Okay, let me stop the recording first.